In this video, I'll demonstrate the importance of appropriate starting point estimates for curve fit parameters in user-defined fits. For nonlinear regression with user-defined fits, the success of the fit depends largely on how good the starting point estimates for the parameters are. If you're able to encode some knowledge about the expected coefficients based on the data points, then the fit is more likely to be successful and the method can work for future datasets. I have some example data that I'd like to fit using this custom user-defined fit equation. First, I'll navigate to mycurvefit.com and log into my account. I'll clear the data field and copy and paste in the X and Y data from Excel. I'll move through the steps of the wizard to identify which column contains my X-axis data and press Apply to confirm the data is organized as expected. Next, I need to update my fit method. I'll open the fit method dropdown and select User Defined. I'll copy and paste in my curve fit equation from Excel and pressing Apply, we can see at a glance that the fit is rather poor for this data set with the default starting point estimates of 1. Opening the Initial Estimates link, we can get a little more information about how initial estimates are used and how they can be specified. We can enter estimates as absolute numerical values or use heuristic expressions to specify a rule of thumb that will be broadly applicable for further datasets. An example outlined here is with a Gaussian bell curve. The A coefficient for a typical bell curve might be the y-axis value at the peak of the curve, which would be the greatest y value. We could, in this case, use a variable max y as a starting point estimate for the A coefficient, which would return the maximum y value of the provided calibration data. If we scroll down, you can see additional information on the variables available for reference and conditional expressions for more sophisticated estimates using a conditional if operator. For this data set, I'll enter a fixed value for parameter b. I know from previous analyses that a good starting point estimate for parameter b is 0.5. However, if you're unsure where to start exploring how the parameter values impact the shape of the curve, please see our video providing tips and tricks for optimizing your starting point estimates. Once I've entered the value 0.5 for parameter b and pressed Apply, you can see the curve fit is much improved with our r-squared value being quite high. I have one more example. In this case, I'll use the 5PL equation, but I'll be entering it as user-defined to allow more control over the starting point estimates. I'll clear my data from the data field and copy and paste in my new data set from Excel. I'll specify which column contains my X-axis data and press Apply to confirm the data is organized as expected. Back up in the user-defined fit method field, I'll copy and paste in my curve fit equation from Excel and press Apply. I'll also update the X-axis to logarithmic, as is typically used for 5PL curve charts. So you can see with the default starting point estimates of 1 that the fit does not appear to appropriately model the data. I'll add starting point estimates to my A and D parameters using heuristics. I'd like the initial estimate for parameter A to be the minimum of my y values, so I'll enter min y. And I'd like the initial estimate for parameter D to be the maximum of my y values, so I'll enter max y. Pressing Apply now shows an updated fit that is a much better model for my dataset. Because we used heuristics in this example, the parameter initial estimates will automatically update for new datasets to use the minimum y value as the starting point estimate for parameter A and the maximum y value as the starting point estimate for parameter D. If you have any questions about initial estimates for your user-defined curve fit parameters, please email us at support@myassays.com.